and would like to welcome you to this forum round table, The Future We Must Plan For. We are live streaming this. It'll also be recorded to enable people to view it later on YouTube. Before I start, I'd like to convey a message from our President, Nick Lowe. Unfortunately, my family and personal circumstances prevent me from participating today, but I'd like to add my warmest welcome to the distinguished presenters at this most timely forum and to the audience who plainly care strongly about the current environmental crisis, which, as I am sure you will learn during the forum, extends beyond even the coming catastrophe of climate change. Planning for this forum started last year, when this country was in the middle of one of the most severe droughts on record. Since then, we have experienced bushfires on an unprecedented scale and intensity, followed by floods, the collapse of the fishing industry off the east coast of Tasmania, and a pandemic that is delivering crippling social and economic impacts. The events of the last year have provided unexpected and severe shocks most policymakers and planners never anticipated. So it is timely to ask what future we must plan for. Although TFM's primary interest is in transport, today's topic will be of interest to everyone, including policy and decision makers and business and government at all levels. So we have invited people from a wide range of backgrounds to attend. COVID has restricted the number of people who could attend today, so we've decided to run this as a round table and have invited people to join the speakers and participate in discussion following the formal presentations. Whilst many people will argue that technology will play an important role in determining our future, it has been very clear for a long time that environmental change will be the dominant factor that shapes our future. And that in turn is strongly influenced by human activity. It is true, we do have a climate emergency, and our first speaker, Professor David Karoly, will discuss this, but it goes much deeper. And that will be the subject of our second presentation by Professor Steffen. This will be followed by a presentation on the politics of change and discussion about how we may respond. We will take a 10-minute break at 2:45, and then we will return and we will have two presentations from Adam Bant and Sally Capp, followed by a roundtable discussion with the panel, followed by question time when we will invite questions from the audience. Those in the virtual audience can forward questions using the chat button with your name and the person you would like to respond. Now, our first speaker. Professor David Karoly is recognised internationally as an expert on climate change and climate variability. David is leader of the Earth Systems and Climate Change Hub in the Australian Government's National Environmental Science Program based in CSIRO. He is also an honorary professor at the University of Melbourne. Professor Karoly was a member of the National Climate Science Advisory Committee, which delivered its final report, Climate Science for Australia's Future, in 2019. During the period of 2012 to 17, he was a member of the Climate Change Authority, which provides advice to the Australian Government on responding to climate change, including targets for reducing greenhouse gas emissions. He has been involved in the assessment reports of the Intergovernmental Panel on Climate Change in 2001, 7, 14 and 21 in several different roles. He was elected as a Fellow of the Australian Academy of Science in 2019 and was awarded the 2015 Royal Society of Victoria Medal for Scientific Excellence in Earth Sciences. Please welcome David.
Thank you, Roger. Now you've got to log in and you've got to get it back. So let me start by, first of all, thanking Roger for allowing me to come along. Yeah. And I'm going to start with my mask on, not because I like speaking through a mask, but because there is some very valuable climate data on the mask. It shows the annual temperatures for Australia in colour, with the reds obviously being hotter annual temperatures and the blues on this side being cooler annual temperatures each year from 1950 to 2019, with obviously the hottest temperatures in 2019. I'm going to come across that. If anyone wants one of these, you can contact, and I'm not selling them and I get no money. They were put together by the Australian Meteorological and Oceanographic Society. And so you can, if you want to, the website is www.amos.org.au. I don't get any money for it, but they are a really interesting climate-related, how would I say, mask. And a lot of people have said, where did you get it from? Well, I didn't make it. They're produced in Australia. They're not made in China. But now I'm going to take it off because I get very hot talking behind the mask. So what I'm going to do first of all, if I can get this to work, is to get up to... That's going to work much better when it's a full screen, I think. So thank you, Roger, for the invitation. You and I talked about this, and what I'm going to try to do in 20 to 25 minutes is cover the history of climate change from 800,000 years ago to 100 years into the future in 20 minutes. And that means I've got to cover things pretty quickly. I'm going to talk about essentially these temperature variations over the last 100 years. I'm also going to talk about the value or importance of young people's involvement and concerns about climate change, because climate change is going to affect the younger people much more. And the School Strike for Climate, which is the photo on the left-hand side, demonstrates that there is a wide group of community that is interested in these sorts of activities. I'm going to start with the summary of my talk. But this is a summary of my talk from 2007, from a United Nations group, United Nations Foundation in the United States, which produced a report called Confronting Climate Change, Avoiding the Unmanageable and Managing the Unavoidable in 2007. The conclusions then are exactly the same as what I would say now, and that's why I'm using it, but it's 13 wasted years of limited global action and greater impacts on global temperature increases. So let me just say, yes, we knew 13 years ago global climate change has been driven by burning fossil fuels and land clearing. It's a growing threat to all countries and will affect both developed and industrialised countries. There was already significant harm from climate change 13 years ago, and further damages are a certainty. And the challenge now, and was 13 years ago, how to keep climate change from becoming a catastrophe. Now, I'm going to leave it to Will to talk more about the catastrophe that's imminent, but it was imminent in 2013, and countries did, am I allowed to say bugger all?
Yep.
I think that's probably the most appropriate description in the Australian context. Let's go back 800,000 years from ice core data collected in Antarctica, which shows both temperature variations and greenhouse gas variations. The top curve is the carbon dioxide concentration from ice core data in Antarctica. The bottom curve is estimates of Antarctic temperatures, again from the ice core data. We can see the slightly warmer periods and the cooler periods associated with the ice ages and interglacial periods that occur about 120,000 years apart. And the most recent temperature variations, where's the mouse gone? Oh, here we go. We have been in an interglacial period, a relatively warm period for the last 10,000 years. And in between that and the previous warm period, about 120,000 years ago, we've had a glacial period. Temperatures in Antarctica were about 8 to 10 degrees colder in the glacial period. Globally, they were about 5 degrees colder. And now I move sideways a little bit. There is only one indigenous population in the world that has survived the temperature variations from the middle of the last ice age to the current interglacial period. That is the Australian indigenous communities that have survived for 65,000 years. And their stories and songlines tell us about the magnitude of climate change. Due to these ice age to interglacial variations, they have survived 5 degrees of warming. They can talk about, and do talk about, the 100 metres of sea level rise from the depths of the last ice age to the current interglacial. And their management of country allowed them to survive those changes. But the temperature change occurred over thousands of years. We're looking at 5 degrees of global warming within the next 100 years. It's 10 to 100 times faster rate of change than we've ever seen before, than humans have ever seen. So I want to acknowledge the traditional custodians of the land on which we live, because we, as Western scientists, can learn from them a lot about how to deal with climate change. They've coped with it. We haven't yet. And unfortunately, we've got a long way to move to understand it. So we can see these changes. We can see, if we look at the carbon dioxide concentration, that at no stage in the last 800,000 years were carbon dioxide concentrations higher than about 300 parts per million until the last 100 years. And in the last 100 years, we've seen an increase now to 410 parts per million. From previously 300 parts per million, a growth of 40% in 100 years. Previously, that 100 parts per million growth took thousands of years. We're seeing rapid change. We're seeing the rapid change in the temperatures, and those increases in greenhouse gases have led to increases in temperature globally. We know that there's large year-to-year variability, but we also see that, and I'm going to talk about this more, that there has been pronounced increases in temperature superimposed on the year-to-year and decade-to-decade variability. And temperatures now, over the last 5 years, are already 1.1 degree above pre-industrial levels, and we're heading rapidly to exceeding 1.5 degrees and 2 degrees, the limits that were set for the Paris target. The second graph here is what I believe is the most important graph that all people need to look at, and that shows, not over the last 100 years, am I allowed to move around?
Of course you are. We won't hear you on the mic, that's all.
Okay, I'll point here and hope that it will work okay.
You can take the mic with you.
Yeah, well, this cursor, we don't have a big stick, do we? I'm going to just point and talk loudly. My voice has been known to be direct. I'm going to talk about this graph. The circles are the carbon dioxide variations over the last 1,000 years, again from ice core data from Antarctica. And what we see, 280 parts per million, and then exponential growth. We've heard a lot about exponential growth with COVID and impacts of COVID. This is exponential growth in carbon dioxide due to burning fossil fuels and land clearing. How do we know that it's not just natural variability, not due to carbon dioxide coming out of solution in the oceans? And that's because of this mirror image curve. That mirror image curve is the fraction of the carbon isotope carbon-13 relative to the carbon isotope carbon-12 in the carbon dioxide in the atmosphere. Carbon-12 is preferentially taken up in plants by photosynthesis relative to carbon-13. What this means is that we can tell that this rapid drop is due to carbon dioxide from plants, carbon dioxide from burning fossil fuels and from land clearing. There is no other explanation. We know for sure that this increase is due to human activity. It's nothing to do with the favourite causes of Andrew Bolt or Alan Jones. They want to talk about anything except the truth. Although I guess that we can talk about multiple truths if you follow the former President of the United States. Let's now go from global temperature variations to Australian temperature variation. Remember I talked about a warming of 1.1 degree over the last 100 years? Let's look at what's happened in Australia. Well, in Australia, there wasn't much temperature variation, lots of year-to-year variability, but no temperature increase until the 1950s. And then from 1950 to the present, we've seen about 1.4 degrees of warming. In 70 years, not 120 years. In other words, the rate of warming is double in Australia compared with the global average. Now, that's not surprising because the global average includes warming over the oceans, and we know that warming over the oceans is much slower. Australia, predominantly, where these temperatures are measured, is all land-based temperature observations. Land warms up faster than the oceans, and we should remember that most people are not fish. Most people live on land, and we need to worry about the fact that when we talk about global warming, almost no one talks about the land average warming. They talk about the global average. Global average is about 1/3 slower than the land averaging warming, or switch it the other way, the land average warming is almost 50% higher than the global average. That's critically important. That's why Australia is warming up faster than the global average. What about when we go to rainfall? Well, we need water to drink, we need water for our ecosystems, and we need water for our agriculture. That climate change has led to major changes in rainfall patterns over Australia. This graph shows the rainfall patterns. I can see it, but it's not showing up there. Top left-hand slide shows the rainfall departures for the last 20 years, or the rainfall for the last 20 years, in a graphic that compares that rainfall to all of the 20-year periods since 1900. And the red colours are for the record lowest rainfall over the 20-year period. The orangey colours are when it's in the lowest 10% of decades. What we know is that in the cool season, the April to October period that's shown here, the 20-year average rainfall in the cool season, southwest Western Australia, Victoria and the east coast of New South Wales was at record lows. We can contrast that with what happens in the warm season. And unfortunately, the lights are washing out most of these colours, which are the blues, and they will show up better in the video, I believe, than they will show up on the graphic. But this shows the same analysis for Australia for the warm season, and this shows increases in rainfall over the last 20 years. Highest rainfall for this decade, or two-decade period, compared with all the other two-decade periods. And there's been an increase in rainfall in much of northern Australia, and particularly all of Western Australia. So the rainfall patterns are very different between the cool season and the warm season. Cool season, decline in rainfall; warm season, an increase in rainfall. I'm going to talk more about that a little bit later. If we want to decide what we can use to predict the future, we can look at crystal balls, but my discovery is that when you look at a crystal ball, you mainly get a reflection of yourself, and you don't get good information about future climate change. But we can use climate models, and if we want to test climate models and how well they predict century timescale variations, we can look at climate model simulations over the last 100 years. The 100 years from 1900 to 2020, and use and compare that for Australian observations compared with the information for Australia extracted from the global climate models. That's what this graphic shows. And again, I've got a much better view on the computer than it is on the screen here. Maybe it shows up. There is a bluish band in here. Does that show at all? Or is Oh, I can't see it from here because it's excellent, excellent. Because that blue band shows the climate model simulations with increasing greenhouse gases for the decade-to-decade temperatures. The black wiggly line is the year-to-year temperature variations. And yes, 2019 is highlighted as the hottest temperature over the last 120 years. The decade-to-decade variations lie pretty well within the model simulations. And this is what you get. These bands down here are the model simulations with no increases in greenhouse gases. They cannot explain the observed warming over the last 50 years. The only way to explain that increase in Australian temperatures over the last 50 years is due to the increase in greenhouse gases. And if we want to look at the period from now until 2040, there is continued warming. And the most recent climate model simulation, shown with this yellow band, actually shows even faster warming than the previous generation of climate models, which are shown by the dash band. It's actually getting worse. Not because of higher emissions, it's getting worse because the climate models are getting better. What else can we look at in terms of comparisons between observed variations and model simulations? Let's look at rainfall. I'm only going to look at the far left-hand one. That's the climate model simulations for Victorian rainfall. I'm biased because I sit and stand in Victoria at present. We've seen a pronounced decline in annual rainfall in Victoria, like I showed before for the cool season. And the climate model projections are, in fact, again, maybe you can see it better than I can, there are in fact triangular bands that you can see, which are the projections from 1985 right up till 2030. What we see is that the observed changes are lying at the worst case. The most rapid model projections of decline in rainfall. They agree, but gee, you've got to take the worst case if you're trying to get the best estimate of what's happened recently. These bands don't show up very well either, but that's all right. I can see it and I know what I'm looking at. These are two separate global climate model projections right up to 2100. Remember I said I was going to go from 8,000 years ago, 800,000 years ago to 100 years in the future. These are climate model projections, the same ones that have been used for simulating the most recent century, now looking 100 years in the future. Looking at two separate cases. The lower one is for rapid emission reductions. And I'll talk about what those emission reductions have to be to simulate that in just a couple of minutes. And the second case is business as usual. Business as usual in this case is no emission reductions and basically burning fossil fuels as fast as possible based on estimates from, say, 1995 to 2000 period. It's important to understand that this graphic, the temperature scales right on the left-hand side, is taken relative to the 1990s. So this scale, which seems to go at about 1 degree here, is actually 1 degree relative to the 1990s, but 1.8 degrees relative to pre-industrial. It's almost set on 2 degrees already, and this only just, on best estimate, limits global warming to below 2 degrees. The high warming estimate and its uncertainty range, the high warming estimate is 4 degrees relative to the 1990s, nearly 5 degrees relative to pre-industrial, and if you come up here, which is the uncertainty range, there are actually reasonable chances that global temperature estimates will be above 5.5 degrees above 1990 levels, more than 6 degrees above pre-industrial. The planet and humans have never experienced global temperatures of 6 degrees above pre-industrial level, because the human population has only existed on this planet for of the order of 200,000 years. And we're talking about 3 million years ago or 4 million years ago to get back to those sorts of temperatures. This is a summary of the projections. I'm going to finish up in a couple of minutes. I'm going to race around this curve in an anti-clockwise direction. We know that global temperatures are going to continue to rise. We know that sea level is going to continue to rise. We know that there are going to be more marine heat waves and more heat waves affecting people on land. We know that these are going to lead to longer fire seasons, more heavy rainfall and erosion, because when the temperature's warm, there's more moisture in the atmosphere. Unfortunately, as I've said already, the cool season rainfall in southern Australia is going to continue. So what do we have to do? Well, what we have to do if we want to limit those impacts is to reduce greenhouse gases. This is what we have to do to limit global warming to below 2 degrees Celsius. And it says here that the carbon dioxide equivalent concentrations for this scenario are to limit the carbon dioxide equivalent concentrations to 430 to 480 parts per million. Carbon dioxide equivalent. Will's an expert climate scientist. Well, Will, what's the carbon dioxide equivalent concentration at present in the atmosphere?
It's around 500.
Well, it's actually near 510 parts per million at present. We have already exceeded, and that means we have to suck carbon dioxide and other long-lived greenhouse gases out of the atmosphere if we're going to limit global warming to 2 degrees. So let's move on to the next slide. What can we do? Well, there's lots of readily available solutions to limit global warming. They do not include continuing to burn fossil fuels. We need to use energy more efficiently. We need to switch to zero carbon energy sources. We need to increase carbon sinks through vegetation and other technologies like carbon capture and storage. And we need to recognise that this will require lifestyle and behavioural changes. We've had lifestyle and behavioural changes with COVID-19. The economic impacts of climate change in 2050 in a recent Deloitte Access Economics report are expected to be in 2050 and every subsequent year greater than the economic impacts in 2020 associated with the COVID-19. So not just 1 year due to COVID-19, every year after 2015 will be bigger, as big as COVID-19 and continuing to get bigger and bigger in the future. What can we do? Well, they also say that economic growth, if we address climate change, will continue to grow at 2 to 3% per year, not fall by 3% per year, which is what happens due to climate change. So, all countries got together, sought to address climate change, came up with the Paris Agreement in 2015. We can see the impact of the Paris Agreement in this graphic, which shows emission reductions. The first international climate agreement was in the 1990s. Emissions in 2015 were in fact up here 60% higher than the 1990s. And what do we find after Paris? Not emissions falling, emissions accelerating in growth after the Paris Agreement. That's not the best way to solve climate change. I'm going to skip over this graphic. It's a summary from all the science-based organisations that reported to the UN in September 2019 in the Climate Action Summit. It summarises everything that I've said in a graphic, but now in words. But the important part is what's over here. What do we have to do in terms of reducing greenhouse gas emissions to meet the Paris Agreement? The simple solution is if we want to limit global warming to 1.5 degrees, what do we have to do? You either have to massively invent vacuum cleaners. I've talked to Dyson, but they don't have them yet, that will suck out carbon dioxide from the atmosphere, and you have to do it rapidly. Or you have to triple the existing Paris Agreement commitments. And that means for Australia, sorry, not triple, I've got it wrong, 5-fold increases. in emission reductions by 2030. What does that mean for Australia? We have to be sucking out. It's easy to work with 25%. We have to be at 125% emission reductions. That means sucking out 25% of our emissions, not just going to zero. It means going to minus 25% in 2030. That's impossible. Even the Prime Minister would agree that's impossible. Key messages. I've taken too long. Yes. No, it's not all right. I've taken up some of the important time for Will and for Robin. But let me finish here. We know that human influence on the climate system is clear. This is not my conclusions. These are conclusions from the IPCC. We know that if we don't reduce greenhouse gas emissions, if we don't get to zero emissions, we're going to more severely disrupt the climate system. We're going to have increases in global average temperatures, and the risks will be severe, and some of them will be irreversible. And Will's going to talk a lot more about that. But we could fix it if we really wanted to. We know how to do that now. I hope that I've given enough of a starting point for Will to take over in a second. Thank you.
Thank you, David. As I said earlier, it's important to understand the dimensions and scale of global change that confronts us. Humanity has disturbed the carbon cycle, and this is reflected in greenhouse emissions and global warming, but we have also disturbed the Earth system in other ways, and the implications are profound. Will Steffen is an Earth system scientist. He's a counsellor on the publicly funded Climate Council of Australia that delivers independent expert information about climate change. He's an emeritus professor at the Australian National University in Canberra, a senior fellow at the Stockholm Resilience Centre in Sweden, and a fellow of the Beja Institute of Ecological Economics in Stockholm. He is the chair of the jury for the Volvo Environment Prize, a member of the International Advisory Board for the Centre for Collective Action Research in Gothenburg University, Sweden, and a member of the Anthropocene Working Group of the Subcommittee on Quaternary Stratigraphy. From 1998 to mid-2004, Will was Executive Director of the International Geosphere-Biosphere Programme based in Stockholm. His research interests span a broad range within climate and Earth system science, with an emphasis on incorporation of human processes in Earth system modelling and analysis, and on sustainability and climate change. Thank you, Will. Please welcome Will.
Right, thanks very much, and thanks for the invitation to be here. Now, if I can work this out, we will get going.
There we go.
Right, so let's see if I can.
You better put it on full screen.
Have we got it? There we go. Now, right. Mine follows on very naturally from David's because I've got a slide from the next generation as well, talking about what's happened in Australia in the last year or so. But I want to take the analysis a little bit further to talk about what the risks are at the Earth system level of exactly the things that David has been talking about, where we are going. I can go through this slide very, very quickly because he's shown a longer version of this. This is only the last 400,000 years, and this is looking at global average temperature. And as David mentioned, fully modern humans have been around for about 200 to 250,000 years. We've been through two of these cycles. And as David pointed out, the only society we know of that's actually gone through the transition from, see if I can get, from through the last ice age, about 65,000 years ago, all the way through to the present, are Indigenous Australians. Point I want to make is this last 11,700 years has been a planetary sweet spot for humans. It's only during this time we've developed agriculture as we know it today, more complex societies with villages, cities, and so on. So if I can work this. So look at the last 100,000 years of most of the last ice age. We can see temperature dropping to the so-called last glacial maximum, which is 20,000 years ago. Then notice the very sharp rise in temperature from about 20,000 years ago to about 11,700 years ago, about 8,000 years. And then the Holocene, the last epoch, most recent epoch in Earth history, which is where we have really developed the societies we enjoy today. David's shown this slide. This is what temperature is doing now, but we need to put that onto a longer term graph to show what this really means. But David mentioned rates, and I'll just want to reinforce them because rates of change are quite phenomenal from a geological perspective. The CO2 increase over the past couple of decades is now about 100 times the maximum rate during the last deglaciation. In other words, it is accelerating. And over the past half century, the global average temperature has risen at a rate about 170 times the background rate over the past 7,000 years of the Holocene. I'll show you that Holocene is seeing some temperature changes, but very, very gentle compared to what's happening now. And over the last couple of decades, temperature is rising over 200 times the background rate and in the opposite direction. But I want to just mention that physical climate system isn't the only thing that's happening to planet Earth as a result of human activities. In fact, it can be argued that we are transforming the biosphere more deeply, more profoundly, and more rapidly than we're actually transforming the physical climate system. There was a synthesis report, an assessment done by a group, it's got a very long name, they're the Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services. Think of it as an equivalent of the IPCC, but for the biosphere. And they came up with some fairly remarkable conclusions. This is not climate change impacts, this is mainly direct human transformation of the biosphere, the living part of the planet. So nature is declining globally at rates unprecedented in human history. And there are a lot of different parameters they use to describe declining. You can think of biodiversity, you can think of ecosystem ranges, you can think of degradation of soils, all sorts of things. Around 1 million animal and plant species are now threatened with extinction, many within decades. So we are entering the 6th great extinction event in Earth history, but the first one driven by a biological species itself. And the web of life on Earth is getting smaller and increasingly frayed. We're seeing more and more instabilities in how the biosphere is functioning. But again, we need to put this in a longer term context. And a colleague of mine from the Anthropocene Working Group named Mark Williams, he works in Leicester in the UK, and he's a paleobiologist. And he was the lead author on this quite remarkable paper called The Anthropocene Biosphere. So he's looking at what's happening during the last 10,000 years compared to hundreds of thousands and indeed millions of years. And he makes this very provocative set of results. Global homogenization of flora and fauna faster than the Earth has ever experienced before. We are now, as a species, commandeering 25 to 40% of the net primary productivity. That is what the biosphere produces every year in terms of biomass and so on, and living organisms. We are now commandeering about a third of that. Human-directed evolution of other species. No other species has ever done that before. And increasingly interaction of the biosphere with the technosphere. Think of plastics pollution. But then he makes what I think is the most profound conclusion, that this is signs of a new third stage of biosphere evolution in the 4.5 billion year history of planet Earth. The first stage was life itself, single-celled organisms, microorganisms and so on. The second stage was more complex organisms, plants, animals, and so on. But he says that we humans are now changing the biosphere directly, so profoundly and so rapidly that this would be looked on, if there were intelligent beings on the planet after we depart, as a third major stage in the evolution of the biosphere. Now, I'll talk in a minute about how these two are linked, but let me jump back to this graph that David showed. This is the graph of what's happening to the global average surface temperature since about 1850 to the present. But I want to put this on a longer time scale. So what I'm going to do now is to go back to about 2,000 years ago and see what climate was doing. So that's the latter part of the Holocene. And you can see global average temperature, that black wiggly line, has been very, very slowly declining. That vertical axis is by about tenths of a degree. Most people put it on degrees, so that's tenths of a degree. And you can see that the climate has been very, very slowly cooling. In fact, it has been since the mid-Holocene. But the envelope of natural variability is about a 1/10 of a degree either side of the average. Now, I've put about a 1 degree temperature rise on there. That's what's driven by human activities. So that's occurred from about 1950 to a little past 2000. And that's not quite drawn to scale. It should actually be a bit higher than that. And you can see the magnitude of change and the rate of change. It's profound, and we've seen nothing like this in the last 12,000 years, and even before that. So now, this is why, if you go back to the biosphere people and their analysis, they are saying that climate change is now the second most important driver of degradation and change in the biosphere. But they also say that 2 or 3 decades down the track, this is going to take over from direct human pressure as the dominant driver of changes in the biosphere. And you can see why that's so. But what I want to do is put the IPCC projections on that sort of time frame. So this is the classic AR5 projections. David showed the low and the high. There were 2 intermediates, the so-called RCPs, the representative concentration pathways. But here we see, again, by 2100, you can see temperatures rising from about 1.8 up till close to 5. Again, the 0 is late 20th century, not pre-industrial. But what I want to do is put this range on that longer time frame that I just showed you. So if we do that, there's the graph I showed you. Temperature about there today. But if we put the IPCC projections at 2100 on the same time frame, they look like that. Your system's never seen anything like this before. This would be a novel state-of-the-art system. So there you see the 1 to 2, 1.5 to 2 Paris agreements, all the way up to the worst-case scenario, which could be 5 degrees or so compared to pre-industrial. So if we now put some markers on that, you can see the Paris targets, 1.5 to 2. That's where that sits. Current trajectory is around 3 degrees or so if we just keep doing what we're doing today. And that's the worst case scenario, 4 to 5 degrees. That's a completely new state-of-the-art system. Homo sapiens and almost every other living creature has never experienced that. And it's a severe challenge even to the existence of our contemporary civilization. But the point I want to talk about now, just sort of the second part of my talk, is the fact that somewhere along that temperature curve, we are going to start tipping various parts of the Earth's system that themselves will accelerate the warming, either through melting ice or putting more carbon into the atmosphere. And the worst case scenario could be they could take the system out of our control. So our current trajectory is that, let's see. Yeah, so if these tipping points take off, sometimes somewhere between 2 or 3, we could lose control of the system and it could go to 4 or 5, even if we get emissions down. So that's the real risk, the existential risk that we face. So let me talk just briefly about what they are. Tipping elements come in 3 different types. They are melting of ice, mainly at the poles, but some mountain glaciers. Circulation changes to the ocean circulation, to the atmospheric circulation, and to the coupled ocean-atmospheric circulation. And biome loss, Amazon, northern forests, and so on. There's been a lot of work done in the last 2 decades. We understand these a lot better. But let me talk now about the Amazon, because I want to bring in biosphere degradation and climate change together. So what does the tipping point of the Amazon actually look like? Well, it arises because of this. The Amazon forest, as its name indicates, it's a rainforest, needs a lot of moisture to maintain itself. About 50% of the moisture, the rainfall, comes from the Atlantic Ocean, advected in from the ocean. But the other 50% is recycled, because the forest transpires during its metabolism, transpires water vapor, which then forms clouds and rains back down again. So it needs both of those sources of water to maintain a rainforest. So it's facing now a double whammy. Climate change, it's changing ocean-atmosphere circulation. And we already see a slowdown of the Atlantic Ocean circulation. That is reducing rainfall over the Amazon basin. In the last 10 years, there have been 3 severe droughts, much more frequent than the long-term record. And that's because of climate change. But at the same time, by the way, that then could lead to dieback, fire, and a savanna-type ecosystem or a dry forest ecosystem. But at the same time, humans are deforesting, and the deforestation rate is increasing with the Bolsonaro government in Brazil. So this is conversion of the forest to cropland or pasture. This reduces evaporation, so it starts reducing that other 50% of rainfall. So basically, the forest is facing a double whammy, and there's concern that within this decade, we could cross a tipping point where the rainfall drops so low that even without any further deforestation by humans, the forest will convert largely into a savanna or a dry forest. Oops. Doing something wrong there. Maybe if I hit that. There we go. Now, these tipping points, we know a lot about them, but the thing is they don't act independently. We have what we can call tipping cascades where one affects another. Let me use the Amazon example. Let's start with a thing called Arctic summer sea ice in the top. We know that is decreasing, the sea ice is melting. That uncovers darker ocean water, that accelerates the warming. That in turn accelerates loss of ice from Greenland. Most of that ice is melting from the top of the ice sheet. That's putting a pool of cold, fresh water on top of the North Atlantic. That in turn is slowing the North Atlantic circulation, and a slower circulation is reducing rainfall over the Amazon. So here you have a pole to equator link, that reducing ice over the Arctic Ocean is leading to a drop in rainfall in Amazon. But we can see all these other arrows, that these are linked. And the concern is that once, like a row of dominoes, you start tipping a few dominoes, you can tip the whole system and basically take the dynamics of the Earth system out of human control. So the IPCC 1.5 report said there is already a moderate risk of what they call large-scale singular events. Those are tipping points, even at 1 degree. But by the time we get to 2.5, and remember we're on track for 3, we're going into a moderate to high risk. This is not a fanciful phenomenon that scientists have dreamt up. It's a real phenomenon, and it's a real risk that must be taken very seriously. So a recent paper published last year by a group of us led by Tim Lenton assessed at where we are on elements of this tipping cascade. I won't go through them, you can read them, there are 9 of them there, but in each of these 9 we already see evidence that they are moving in a direction toward the tipping point. Now we don't know where the tipping point itself lies, but there is real concern that the whole system is starting to move at about a 1 degree forcing. And this quote, I think, is the most important one of that paper. If damaging tipping cascades can occur, and we're pretty sure they can, and a global tipping point cannot be ruled out, then this is an existential threat to civilization. No amount of economic cost-benefit analysis is going to help us. A year earlier, we hypothesized that this could be the case, and we published this little stability landscape that shows the Earth where it is now. It's moved out of the Holocene. It's out of the comfort zone of that interglacial. You can see the glacial states on the left. But as time comes forward, we're sitting at this, pretty much at this fork in the road that's going to probably happen this decade. We can either get our act together, get emissions down, become much better stewards of the biosphere, and move the Earth into what we call stabilized Earth, which would be 1.5 degrees to 2 degrees warmer than today, but stabilized. And we may be restoring the biosphere. That's that very positive scenario. But the other one, if we initiate a tipping cascade and go over a planetary threshold, is what we called hothouse Earth. That's the current trajectory. Greenhouse gas emissions are increasing, temperature rise is accelerating, biosphere degradation is increasing. So we are on that path toward that cliff or that waterfall. So the tipping cascade I talked about is that planetary threshold that we've drawn in this cartoon fashion, like a cliff or a waterfall. Once you get close to the waterfall, the current increases in a river, and you get to a point where you can't avoid the waterfall. And that's the concern, is that sometime, even within the next decade, we may push the climate system and degrade the biosphere to a point where we can't pull it back. And then we go over the cliff. But as I said before, the other path is if we meet the Paris targets, learn how to suck CO2 out of the atmosphere and store it, and start restoring the biosphere, we could change the direction of the Earth's trajectory today. I'll conclude just as David started, with students, because it's their future that we are talking about. This is taken outside of Parliament House in Canberra. I like it very much because I spend a lot of time in Sweden and I like the nice connection with the Swedes there. But the really important one is this one. We need system change. And I think hopefully I can pass over to Robin and she can talk about what sort of system change we actually need. Because it's clear from what David and I have said that our present system is pushing us into extremely dangerous planetary territory, and we need to change. So I'll stop there. That was depressing enough. Robin's going to tell us how we can fix it.
Thank you very much, Will.